So variations in pressure let us breathe. They also help us, variation in pressure, in changes in pressure, help us Earth's atmosphere creates wind and to predict weather. What the heck?
Have your husband translate that in another language?
Variations in pressure help us
Helps Earth atmosphere, or
Helps us create wind. Cool.
help variation. Well, that's not even good because that's changes in pressure help us predict. I don't know. This meteorologists look at changes in pressure to help predict the weather. It's really. So they often are showing patterns like this: high pressure system over here and a low pressure front moving this way. High pressure generally associated with clear weather, sunny and calm. Low pressure, it usually brings unstable weather. Rain, wind, tornadoes, hurricanes, all kinds of good stuff like that. And the instructor getting excited in the next room. If it isn't the trains, it's Mr. Volandi. The number of gas particles in a given volume, or the density of the gas particles, I shouldn't use the word density, the concentration of the gas particles decreases as you increase the altitude. So around here, if we want to, I was going to say around here, if we want to get high, we go to Kings Canyon. If we want to get out of the smoggy air in the valley, we drive up the hill to Kings Canyon. It's higher in altitude. Just quit now.
Are you recording this?
I am recording this. Yeah. Well, it'll be interesting to see what kind of comments I get on this one. Up at Grant Grove in Kings Canyon National Park, you're up at 6,000, 7,000 feet, something like that. The air, we say, is thinner up there, right? And if you go running or something, you're going to get out of breath faster, right? Because there's less oxygen up there. The air is thinner. It's less concentrated. And as you keep going higher and higher in altitude, it gets thinner and thinner and thinner. That's why when you fly on an airplane, the cabin is pressurized. Because otherwise, when you get up to a certain point, you suffer from lack of oxygen and everybody passes out. It's really bad when the pilot passes out too. Gas pressure decreases with increasing altitude. We'll try to get out of that one. Here, 2 mason jars with red gas particles in them. This has a lower concentration of gas particles. It's got the same volume as this one, but this one over here has more gas particles. This is going to have a higher pressure of gas than this one because there are more particles hitting. And it's the particles hitting the container that give the pressure. This explains what happens to your ears when you fly in an airplane or when you go up to Grant Grove. Your ears pop, right? What happens is there's a pressure difference. So inside your ear, you have an eardrum. It's a thin membrane, and it wiggles and allows you to hear. Outside your ear is open to the atmosphere, and inside there is some air, and that is connected to the back of your throat by your eustachian tubes. So as you go higher in elevation, the pressure outside your eardrum is reduced, where the pressure inside remains the same, and it pushes on your eardrum and causes your eardrum to bulge out, and that's not very comfortable. And so eventually the difference will get big enough that this pressure will open your eustachian tube. You can help that out by chewing gum or yawning or just kind of massaging your neck. Try to get that to open and let the pressure out. When you come back down, the opposite happens. the pressure outside becomes greater than inside, and it causes your eardrum to bulge the other way, and then you have to get air to go back in. Personally, I find that's more difficult than getting pressure out. Come down, and there's always one ear I just can't really hear out of for like half a day. And that's why babies scream on airplanes. It's not because they're trying to rule the world or anything. Their ears hurt. Poor things. How do we measure atmospheric pressure? This is a very old device, the mercury barometer, in its simplest form. A glass tube filled with mercury is inverted into a dish filled with mercury. Some of the mercury comes out and leaves a vacuum behind. Why doesn't all of the mercury come out? Pressure difference. There's atmospheric pressure pressing down on this mercury, which is supporting this column of mercury. Inside is a vacuum, no pressure. So the height of this column of mercury reflects the difference in pressure between outside in the atmosphere and that vacuum of zero. And so Torricelli was the guy given credit for developing the mercury barometer. He took one of these and he went up a hill. Big hill, I think. I need to look up the story. I've been making this up too long. He goes up the hill, and as he's going up the hill, he's keeping an eye on this, and the column is shrinking as he goes up the hill. And then you bring the thing back down, hill meaning like Grant Grove Hill, big mountain thing. As you come back down, it goes back up again. That's odd. At this point, they did not know what molecules were. There was no electricity. This is back in the 1600s when this was going on. So this was like crazy cool. They also didn't know that mercury was toxic. This column of mercury is about 760 millimeters tall. And so the original pressure unit was in millimeters of mercury, the height of a column of mercury. And at the average pressure at sea level is 760 millimeters of mercury. If you do unit conversions, you'll find that's 29.92 inches. And so like this little weather station here is telling me that the atmospheric pressure in here right now is 29.46 inches of mercury. So it's a little bit less. It's a little bit of a low pressure. And what's going on outside? It's been raining today. It's a lower pressure. That's why people are always hung up on the barometric pressure. If this pressure is higher, the column of mercury gets taller. So millimeter of mercury, weird unit. It's also called a torr in honor of Torricelli, but we still retain millimeters of mercury. So now instead of torr making things simpler, it just added to the things you have to remember. So a torr and a millimeter of mercury are the same thing. Here are some other units. Yes?
On the previous slide, the tube.
Mm-hmm.
So what happens if you just keep making that longer and longer and longer and longer and longer?
What happens if you keep making it longer and longer and longer? It will still only have 760 millimeters tall of mercury. The rest will be empty.
So just empty, so it can't. But it's a vacuum, so the pressure.
It'll be a vacuum. It better be a strong tube. If you make it too long, out of thin glass, it'll just implode on itself and break.
Because of the exterior pressure.
Well, it'll go a little bit above. It'll go above only if the external pressure is higher. So like if you go below sea level, or you put it in a hyperbaric chamber and put pressure on it, you can get it to go higher. What's kind of interesting, the reason mercury is a liquid at room temperature, the reason mercury is useful here is because it's very dense. Its density is about 13.6 grams per milliliter. You can make a barometer with water,
Has to be very tall.
but it has to be very tall. It's about 34 feet with water. That's because it's a lower density, 13.6 times lower. So I think it ends up being 13.6 times higher.
Do we have liquids with higher density than mercury?
Are there liquids with a higher density than mercury? I don't know. There are metals with higher densities, and if you heated them, they would become liquids with higher densities. But at room temperature, I don't know. It's a good question. Okay, so other units. So I'm going to circle the important ones. Torr. Oh, wait. I didn't mean to do that. I take that back. Atmosphere, torr, and millimeters of mercury. Those are the three we're going to run into in chemistry. The rest we will see, but mostly as, let's see if they can convert pressure unit type problems. PSI is one you're probably familiar with. You know, you need to fill your bike tire or your car tire. The pressure is measured in PSI, pounds per square inch. Pound is a force unit, square inch is an area unit. Pascal is a Newton per square meter. So you need to be able to convert between pressure units. So this line you should memorize. It's not too hard. If you need other units on a test, for instance, I will give you this second line. And what's nice about the way this is presented is all of these things are equal to each other because they all equal 1 atmosphere. And so pressure unit conversions are always one step. Isn't that nice? No multiple steps. So your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert it to PSI. What do you think? 30.44, is that going to be a rainy day or a sunny day?
Sunny.
Probably sunny. That's a higher pressure than 29.92. So we're just converting the units. We're going to use the conversion factors. 30.44 inches of mercury. And we want PSI on top, and we want inches of mercury on the bottom. Do you know, does the dot on a lowercase I have a name? Do you know what it is?
I call it the dot.
Well, I call it the dot too, but I'm just thinking it probably has a name. Because I was going to say I'm having trouble with my, and I realized I don't know what that's called. I'm having trouble focusing on one subject too. Just stick the unit that you want on the top, the unit that you have on the bottom, and then go look at the table. So what do I got here? Inches of mercury, 29.92. And PSI, 14.7. $30.44. Tittle? With Tittle?
Yeah.
Okay.
Yeah,
That's probably why we don't say it that much. I wonder if that is associated with titillating. But how would that be? The dot on an I is exciting? I don't know. I'm standing here talking to you about gas units, but my brain is also going off in all these different places. 14.955 PSI. How many sig figs? 3. So 14.7 PSI, is that exact? No, it's not exact. Are any of them exact? This one is. The 760 is exact. And of course the 1.
15.0.
Well, torr and millimeters of mercury are exactly the same unit, it's just a different name. So when you're converting 1 atmosphere to torr or to millimeters of mercury, that 760 is an exact number. So it's just whatever sig figs you started with is what you get. So for this one, I need 3 only. So that would be 15.0 psi. I got my tittle. Oh yeah, because there's a jot and a tittle. I wonder if the jot is the cross on the T. You want to look that up? Every little jot and tittle, right? Any questions?
Yeah,
Are we done yet? Pardon me? Yeah, dot your I's, cross your T's. That's what I'm thinking, it must be jot. We're not going to get as far as the Wednesday people did. Oh well. We do need to talk about the manometer. I'll try to rein it in. Barometer measures atmospheric pressure. Manometer measures pressure in a container. So here we have some sort of a container with a gas in it, and we want to know what the pressure is. We can attach it to a U-shaped tube. I don't call them U-tubes anymore. It's a U-shaped tube with mercury in it. If both ends of this tube were open to the atmosphere, the mercury would just sink to the bottom and the level would be the same on each side, in each arm, right? But it's not the same because this is essentially blowing into the straw and pushing the mercury up on the other side. So this pressure on this side is greater than the atmospheric pressure on that side. This height difference between the high and the low gives us the difference in pressure between the inside and the outside. It doesn't give us the absolute pressure, it gives us the difference. So we still need to know what the atmospheric pressure is, and then we would add this difference. You know, let's just say that this was, let's just say it's 11 millimeters, that difference. And that outside we are on an average day at sea level and it's 760 millimeters of mercury is the atmospheric pressure. Then what's the pressure inside here? (760 plus 11). 777. Ooh, no. 771 millimeters of mercury. That would be the pressure in here. I can tell that this pressure is higher because the side attached to the container is lower. That pressure is pushing this down, which causes the other side to rise up. If this pressure was lower than outside, the mercury on the atmospheric side would be lower and on the container side would be higher. Questions?
Why do you add the 11 millimeters of mercury?
Why do I add instead of subtract? Well, that's what I was trying to explain, but I didn't do a very good job. This pressure is greater than outside because this side is lower. So, you know, it can be confusing. Well, this side's lower, the pressure must be lower. No, think about why would this go down? Because this is blowing on it, it's putting pressure on it, right? It's putting pressure on this side, forcing that side up. If this pressure was lower, then it would be sucking the liquid up, the atmosphere would be pushing down on it, and this side would be lower, and that side would be higher. Then you subtract.
So it's an increase in the pressure over the
Yeah.
pressure.
The difference here reflects the difference in the inside and outside. It doesn't reflect the absolute pressure, and so you have to use a little common sense to identify, do I add or do I subtract? You're welcome.